subject is engineering chemistry. Types of ion exchanges. Topic name is types of ion exchanges. My name is Sai Chen. I am from Computer Science and Engineering, Data Science Department. Introduction to ion exchange. Ion exchange is a reversible chemical process where ions are swapped between a solid materials and a liquid solution. This process is widely used in water purification, chemical separation, and industrial catalysis. This process mainly used in real life or domestic purpose can used in to use water purification and chemical separation, industrial catalysis. Ion exchanges are materials that facilitate the transfer of specific ions while retaining others. The technology plays a crucial role in softening water by removing calcium and magnesium ions. This technology removing this technology has used to softening of water and removing chemicals calcium and magnesium from the ion exchange process. Understanding ion exchanges is essential for applications in environmental and process engineering. Basic mechanism of ion exchange. Ion exchange occurs when mobile ions in a solution are attracted to fixed charged groups on a solid matrix. The solid matrix, typically a resin contains functional groups and release ions in exchange for others. For example, sodium ions and a resin may be released to replace calcium ions in hard water. This process is reversible and can be regenerated using concentrated salt solutions. Equilibrium and kinetics on how efficiently ions are exchanged in practical systems. Next, classification of ion exchanges. In this process, the classification of ion exchanges are broadly classified into main two types categories: cation exchanges and anion exchanges. There are two types of resins. First is cation and next is anion. This cation exchanges release positively charged ions and attract negative sides of the matrix. This cation exchange releases positive side ions. This is known as cations, and same another way ion exchanger release negative charged ions. So it is called an anion attract positive sides of the matrix. So it is called an cation and anion exchanger. This is our two types calculation in ion exchangers, cation and anion. Each type can be further divided based on the strength of the functional groups attached. Some advanced systems use mixed beds combining both cation and anion exchange resins. Cation exchanges. First one, cation exchange resins. Cation exchangers contain negatively charged and functional groups that attracted cations from solution. In this previous slide, we said the cation exchanges contain negatively charged functional groups. So it is called as cation exchange resin. So common functional groups include sulfonic acid, S3OH, SO3H, and strong acid cation SAC resins. In this case, weak acid cation WAC, known as WAC weak acid cation resins, are carboxylic acid groups. COH groups are present in the cation exchange resins as well as higher pH values levels. SAC means strong acid cation. Resins can exchange ions like Ca2 plus, Mg2 plus, and Na plus. These three chemicals are exchange ions is in cation exchange resins that are Ca2 plus, Mg2 plus, and Na plus across a wide pH range. These resins are commonly used in water softening and deionization systems. Next, anion exchange resins. Anion exchange resins are positively charged functional groups that attract retain anions from solution. Strong base anion resins are quantumary ammonium groups that function effectively across all pH levels. Weak base anion resin contain tertiary amine groups and work best in acidic conditions. The WPA resins are often used to remove strong acids while allowing weak acids to pass through. Strong acid cation SAC. SAC resins are highly effective due to their ability to dissociate completely in water. They contain sulfonic acid groups that release H plus or Na plus ion during exchange. These resins can operate in acidic, neutral, and alkaline environments without losing capacity. Common applications include boiler feed water treatment and pharmaceutical purification. In compare, common applications are boiler feed water treatment. In this, regeneration is typically done using hydrochloric or sulfuric acid solutions. Weak acid cation, WAC resins. They have a high affinity for divalent cations like Ca2 plus and Mg2 plus, especially in natural waters. These resins offer high exchange capacity but require alkaline conditions to function efficiently. They are often used in combination with SAC resins for high efficiency softening. Regeneration uses strong base anion SBA resins. They effectively remove both strong and weak acid anions such as Cl minus, SO2 minus, and HCO3 minus. Weak base anion. They are selectively remove strong acid ions like sulfate and chloride while ignoring carbonates. Chelating ion exchanges. In this case, chelating resins selectively bind metal ions through multiple covalent sites. They form stable ring-like structures, chelates, with transition metals like Cu2 plus, Na2 plus, and Fe3 plus. Inorganic ion exchanges. In inorganic exchanges, including materials like zeolites, clays, and synthetic zeolites have a porous crystalline structure that traps cations such as Na plus, K plus, and Ca2 plus. Organic versus inorganic exchanges, applications of water treatment, ion exchanges widely used in soft and water removing, CAT plus and Mg2 plus ions. Applications in chemical industry, ion exchanges act as catalysts in esterification and hydrolysis reaction with introducing impurities. In this diagram, we can see clearly ion exchanger, what is ion exchanger capacity and exchanger resins. This is three resins in the store of water, softening of water, removing Mg plus 2 and Ca2 plus ions from the ion exchanger process. Regeneration. Regeneration means the process involves backwashing, chemical dosing, slow resin, and fast rinse stages. Regeneration resources the ion exchange capacity of exhausted resins using concentrated salt at acid solutions. Advantages and limitations. Ion exchange offers high selectively scalability and the ability to treat large volumes continuously. It produces high purity outputs suitable for sensitive applications like pharmaceuticals and electronics. Future trends and innovations. Research focuses on developing selective resins for rare earth and critical metal recovery. Nanocomposite ion exchanges combine polymers with nanoparticles for enhanced capacity and speed. Green regeneration methods using electrodialysis for solar energy are being explored. Smart resins with stimuli responsive behavior adapt to pH temperature changes. In this case, with AI-driven control systems enables predictive maintenance and optimization. Thank you.